last couple of lessons we've been looking at the fundamental frequencies and the different frequency and standing waves that you get on a stretched string. In this lesson we're going to look at the wave patterns or the frequencies you get from pipes. So you know in my classroom we have a set of pipes, and those pipes are open-ended. And what I mean by open-ended is they're open at both ends. You can see through them basically. If you look down one end you could see out the other end. And when we hit those pipes off the table, each of them produces a different sound. And you'll know that because you've seen it a few times, but they all produce a different sound because they're all different lengths, or they're different diameters, or they're made of different substances and so on. So if they're producing a sound, it means there's a sound wave traveling through them. And that sound that they produce has a frequency or has a pitch, so therefore the sound waves that are produced have different frequencies. So there's, just like the frequencies on a stretched string, there's different standing waves that are formed within pipes. And the easiest way to kind of describe this is if I draw one wave here. So here's a wave, and we know that one wavelength is, you know, one full hill and one from full valley. But when it's a standing wave and it's standing waves that are formed, it's not the same as a normal traveling wave, in that what we have is we have our nodes, we have our points of node displacement, and then we have our antinodes. So basically there's no movement of the particles here at the nodes, but this particle is just constantly moving up and down here to the maximum displacement. Now the one rule you have to remember with pipes is that if it's open-ended, at an open end, or at the end, at an open end, it is only possible for an antinode to exist. This is for our standing waves. So you can't have a node here, and that makes sense because it's an opening, so you couldn't just have a point there where there's no kind of displacement of the particles. So it's easy then to kind of figure out what the harmonics are, because if we use this kind of wave that I've drawn at the start, and it's a good tip to sketch this down if they ask you to draw these in an exam. Where's the first point where we have an antinode? Well, this is our first antinode. And our second point where we have an antinode is here. And between here and here is actually the first pattern that you can achieve, or the first standing wave that can be achieved. Now I'm going to be terrible at drawing this, but what we have is something like this. That's a really bad drawing, but if you look at page 200 in your book you see it a bit better. We have a node in the middle, node displacement, and we have an antinode at this end, and we have an antinode at the other end. Now this pattern, this terribly drawn pattern, is the first fundamental frequency, or the fundamental frequency. The fundamental frequency, or also known as the first harmonic. And that will produce a certain sound, and that sound will have a certain pitch, and let's say its frequency is 100 Hertz. Okay, just as an example. Now a common question they'd ask you would be to find the wavelength of this wave, or to find its wavelength. Now if it's sound travels at a speed of about 340 meters per second, but they'll give you that in the question. And let's say I'm telling you that the frequency is 100 Hertz and we want to know the wavelength. Well, V equals F lambda, so lambda would be V divided by F. So that's one way of doing it, 340 divided by 100. Another way of doing it would be to look at the length of this pipe. And let's assume the length of this pipe is 1.7 meters. Now when you look at this, how much of a wavelength can we actually see? We can see from here, that's half a hill, half a trough. How much of a wavelength is it from there to there? Well, if you look at it, it's actually about half a wavelength. It's lambda over 2. Because you don't have a full peak, you don't have a full trough. So if you wanted to find the wavelength of the wave, the wavelength would be 2 multiplied by 1.7, which is 3.4 meters. So that's another way that you'll be expected to find the wavelength. So that's the first harmonic. Now let's look at the second harmonic. Hopefully my drawing will get better as this goes on. Draw the pipe again. Now the first harmonic was from the first antinode, because we can only have antinodes at the end, to the next antinode. The second harmonic will go to the next antinode. So because we can only have antinodes at the end, so it's only here, and the next possible one will be here. So we draw that pattern in between those two regions, and we get something like, again this is going to be not the best drawing, something like this. We have an antinode at either end, and this time we have two nodes. So this is the second harmonic. And remember, the second harmonic is also known as the the first overtone. The first overtone. Let's say again this was a 1.7 meter long pipe, and they asked you to use that fact to find the wavelength. Well, how much of a wavelength have we got here? So a wavelength is one full peak and one full trough. Well, here's remember that it's doubling up as well, so this would be our trough, and then we have half a peak, half a peak. So this is actually equal to one wavelength. So lambda in this case would be 1.7 meters. Next one, and this is the last one I'll do, and then you can have a look at the notes and see, can you draw the rest of them? So the next fundamental frequency will go from our first antinode, skip our first antinode, skip the next antinode, skip the next one, and all the way to the third one. So the pattern goes from here to here. So we have two kind of loops in the middle and then an opening at either end. So this one could be the best drawing yet. So one loop, two loop, one loop. There you go. So now we have our third harmonic, which is our second overtone. Now what I want you to do in a minute is I want you to actually pause this video, and I want you to try and draw your fourth harmonic and your fifth harmonic, because you actually need to be able to hand draw these in a test. They can ask you. Again, let's say this is 1.7 meters long and they ask us to find a wavelength. Right, well, we've one full peak, one full trough, and then we've half a peak and half a peak. So that would be 1.5 lambda would be this whole thing. It's 1.5 wavelengths. So 1.5 lambda equals 1.7. So lambda equals 1.7 divided by 1.5. And whatever that equals is your answer for lambda in this case. So that's the end of this video anyway on open pipes and harmonics. What I'd like you to do is read page 199 and 200 of your textbook, and I want you, before you even do that, I want you to actually try and draw the fourth and fifth harmonics. And like I just did there, I'd like you to find the wavelength, find lambda, if the pipe is 1.7 meters long. So try that as a little task, but in your notes you want to make sure you have all 5 harmonics drawn, because it does come up as an exam question. Tomorrow then we'll look at pipes where one half is open and one half is closed, and we'll have a little equation that goes with that as well.